Hello class, welcome. This is the presentation from the Warriors. I would like to present our wonderful members, Christopher, Dylan, me, Francis, Sean, and Mario. And we're going to talk about space exploration. Enjoy.
Good afternoon, everybody. My name is Dylan Covell, and I got the S in the STEM, S for science for space exploration. Our group name are Warriors, and this is my presentation. It's a pretty broad presentation. It's not like It's not based on a simple one topic, if you know what I'm saying. And yeah, so we'll go ahead and get into this. Table of contents. This is kind of just show us what we're going to be learning about here in this presentation. First is going to be the introduction to space exploration itself. The next is going to be methods of planet discovery. After that, it's going to be planetary diversity. Then it's going to be a history of planet discovery. And then we're going to explain some light years, talk about exoplanets, talk about the habitable zones, and planetary atmospheres. All right, let's get into this. All right, introduction to space exploration. Space exploration is a scientific pursuit of discovering and understanding outer space beyond Earth's atmosphere. It involves a wide range of scientific principles and technologies from physics and astronomy to engineering and computer science. Planet detection also plays a huge factor. This is because if we find a planet that we're not too sure about, why would we discover it? You know, there's just many questions that people ask about space exploration. That's just one of the big ones. All right, continue on here. Methods of planet detection. There's a transit method, the radial velocity, and if you want to, you can read the definitions. I'm not going to go into depth about those, but there's four total different types. There's those two: the transit method and the radial velocity. This is an image of radial velocity. I can't explain it. If you want to stop the video and read it yourself, you can. But this is what I got. The next two methods of planet detection are direct imaging and gravitational microlensing. Once again, if you want to read the definitions and everything, to kind of get a better example of it, there's the definitions, and that picture in the bottom right is actually the exoplanet Beta Pictoris b, which is part of the definition of direct imaging there. This is an image of gravitational microlensing. Once again, if you want to pause the video, you can kind of read it. I'm not an astronomer, or anything, because I have no idea what this means. I'm not even like a good science guy. So this is all. If you want to read it and pause it, you can read it. I'm not going to explain anything about it, but this is what it means. Planet diversity. Variety of planet types. There's a bunch of different varieties. There's the super Earths, which is larger than Earth, but it is a habitable planet in the habitable zone. Mini Neptunes, which is a gas giant that has a thick atmosphere, or sometimes with vapor or clouds. Ice giants, as you know, as it says, it is an ice giant. Varying compositions and atmospheres. This is the super Earth. It's just an example. A mini Neptune. It looks like Neptune. Well, that's probably not an exact good picture there. Ice giant, and that kind of explains what an ice giant is. History of planet discovery. So ancient civilizations, they kind of had their theories, but then we really started exploring space around the 20th century. In 1957, the Soviet Union launched Sputnik 1, which was the first artificial satellite, beginning of the space race. In 1969, the United States, landed on the moon with Apollo 11. This marked the first footsteps on another celestial body. And now going to today, they're trying to go back to the moon in the later 2020s and go to Mars by the 2030s. This is an image of Sputnik 1. Light years defined. Light year is a unit of distance used in astronomy to measure vast distances in space. About 299,792 kilometers per second, or 186,282 miles per second. In numerical terms, one light year is 9.46 trillion kilometers, or about 5.88 trillion miles. And I got a picture of Buzz Lightyear down there, so I couldn't find an actual picture of a light year. Exoplanets. Exoplanets are just planets that are not Earth, or any planet that's out of our solar system. So there's confirmed 5,300 exoplanets and over 4,000 planetary systems. The first one that we discovered was in 1992, orbiting pulsar PSR B1257 plus 12. That's a weird name for a planet, but sure. Goldilocks zone and the habitable zone. It's pretty much not too hot, not too cold, all that good stuff. Exoplanets were in a zone of great interest because they could potentially support life as we know it. Kepler 452b is Earth's cousin and is an exoplanet discovered in the habitable zone of a star very similar to the Sun. It's about 1,400 light years away and roughly the same size as Earth. You guys can read this one if you want to. I'm not going to really go into depth about the planetary atmospheres and potential for life. We're going to go ahead and skip this one. This is an image of what that was just talking about. So once again, if you want to pause the video, you can go back and kind of look at it yourself. James Webb Telescope. That's it's already provided important data on the atmospheres of exoplanets, including detecting water vapor, carbon dioxide, and methane on planets. It was launched in 2021 in December and is one of the highest quality telescopes that we've ever launched into space, which is very good for the science aspect of us discovering space exploration. This is the James Webb Telescope. It's kind of a decent picture. There's better pictures out there, but this is the best one I could find. Conclusion: discovery of exoplanets has fundamentally changed our understanding of the universe. With thousands of planets now confirmed, scientists are beginning to piece together how planetary systems form, what conditions are conducted to life, and whether we might one day find an Earth-like planet where life could exist. The question is, are we alone in the universe? Space exploration. These are my references. You can pause the video if you want to see my references, and that concludes this PowerPoint presentation.
Hello class, my name is Francis Castellanos and I belong to the team Warriors and I will talk about technology area in space exploration. Here's a little quote I found really interesting. The space industry is not just about exploring the unknown, it's about improving life on Earth by Elon Musk. Introduction. First, we need to know what space exploration is. Space exploration is the investigation of what's beyond and outside our planet Earth and get information about everything outside. We can talk about the universe, planets, stars, everything that is outside of planet Earth. Technology is pretty crucial for space exploration. It can help build spacecraft, collecting data, surviving, travel, and everything else. Some other major points I will talk about are the vehicles used for space exploration, ways of communication, how they communicate, the use of AI, instruments they use, and robots. The vehicles is a really important part of space exploration. It can help facilitate astronauts and space team to complete their mission. One of the vehicles used in the Orion, I hope you guys can see my laser here, the Orion. It's a spacecraft from the NASA built in the Artemis program. It includes the crew and the service models and also help and as adapter for emergency for like launches. It's like if the rocket is have any emergency in the space, you just connect to that vehicle and I will help you in going back or anything to help do anything to fix. Another one is the SEV or SEB, or mostly known as Mars vehicle. This one is a pretty interesting vehicle that can travel 10 kilometers per hour, and it contains it can contain up to 2 astronauts, and it can help them survive there up to 14 days with sleeping system and sanitary facilities. Another one is the Getaway. The Getaway this time and for step over for this longer space mission. It helps them stay there for longest to explore more space, the moon, and everything else. Now, the way they communicate. It's pretty interesting the way they communicate. Before, a long time ago, they used to communicate with radio waves. They used to use radio waves doing electromagnetic waves to move from antenna to antenna to communicate with image or just a voice. The one they're most using right now are these two. The DSN is a contains a really large antennas, really big antennas that can travel and transmit high banded data, allowed to scientists and the astronaut to receive image and data information in almost real time. The one that really implementing new right now is the laser communication. It's similar to DSN, but it's travels really faster than anything. It's just like an instant, it's just like a text message. It's really instant communication right there they can get. This is a really interesting era, the AI, artificial intelligence. It's really new. They're using it really new, just as everything else. But space exploration is pretty important right now because it helps to analyze the space data. It helps analyze all the planets that they find and anything else. Also, it prevents to help for prevention for the weather and any meteors that can hit the spacecraft or anything else like that. The, the instruments used for space exploration, um, they have really interesting instruments to use. Both two of them is the telescope, the Hubble Space Telescope, and the James Webb Space Telescope. And this one here, the Hubble Space Telescope, is really old telescope. They launched it to low Earth orbit in 1990. It still remains in operation. It's pretty interesting how they got it so long there, but it helps view more largest and longest distance for the planets and the space observation. And this one is pretty new, the James Webb Space Telescope, that offer insights for information of stars and galaxies. And one another word they use is the spectrometers. They use that for analyze the chemical composition of the planets, the moon, and asteroids. For example, analyzing the rocks and the soil of Mars. The use of robots. Two of them are the Voyager 1 and the Perseverance. This one here is pretty interesting because it's automated. Both are automated, and that one just collects soil from Mars and the Moon just to send the data like, to the Earth, so this scientists can analyze it. And Voyager 1 is pretty similar, but explore like more distant planets and beyond, really extensive planets. In conclusion, and conclusive technology is the foundation for all space exploration efforts. It helps innovation of spacecraft, robotics, AI, propulsion, and life support systems that make missions that before was really impossible now come to reality. Here is my presentation, guys. If you guys have any questions, please leave it in the comments in the forum, and I will try to answer as best I can. Thank you.
My name is Christopher Armentrout. Today I'll be presenting on space exploration, focusing on NASA's achievements of engineering with the Space Shuttle program. The program operated from 1981 to 2011. Over its lifespan, it completed 133 successful missions. While it was overall highly successful, it notably faced two tragic disasters with the Challenger and Columbia shuttles, with these failures paving a safer future for spaceflight. The program revolutionized space travel with the idea of creating reusable spacecraft, which were both cost-effective and versatile, serving as a crew and cargo transport, launch vehicle, and more. The concept of reusability was a vital feature of the Space Shuttle program, but not without its danger, as can be seen with the Challenger, with low temperatures weakening O-rings, leading to bad seals, and then ultimately the collapse of an external tank leading to the catastrophe. But this disaster also led to the establishment of new safety and quality assurance standards within NASA and then within spaceflight. The following disaster, occurring in 2003, of the Columbia led to the cancellation of the program, with the causes being accredited to a failure to consider this accident as a possibility caused by somewhat common foam strikes, the improper internal communication within NASA, low budget, and more issues. While reusability posed many engineering challenges and caused notable disasters, after the disasters, safety protocols were enhanced significantly, increasing turnaround times to 88 days from its previous 54 days before the Challenger disaster. This balance between safety and efficiency was a critical focus for NASA engineers and remains so today with more modern safety engineering in aerospace. The increase in turnaround time reflected the program's safety standards and lessons learned. These challenges ultimately drove innovation and influenced future spacecraft design. The impacts of the Space Shuttle program extended far beyond just its own missions and the engineering challenges it brought. It was responsible for bringing the Hubble Space Telescope into orbit and performing critical maintenance to render it fully operational, and then perform routine maintenance to retain this ability. The shuttle also played a critical role in building the International Space Station, with 36 assembly flights directly supporting its construction. Without the Space Shuttle program, projects like the ISS would have been nearly impossible or far too costly. It also paved the way for modern reusable spacecraft like SpaceX's Falcon 9 rockets, and now, as very recently, the Starship, with many new engineering advancements coming from its 30-year program. These advancements from the Space Shuttle program have fundamentally shaped the future of space exploration forever. Today, private companies like SpaceX are leading the charge with reusable spacecraft and are now taking the first steps towards interplanetary travel. While the shuttle program concluded in 2011, its legacy lives on with the combined ingenuity of thousands of engineers who have created these new standards and discoveries, allowing these advancements to remain not only safe, but effective. So, in conclusion, the NASA Space Shuttle program was an extraordinary feat of engineering and incredibly important to space exploration today, as its successes and failures have left lasting impact on spaceflight forever, revolutionizing the reusability of spacecraft, safety engineering, and general aviation forever.
This is the escape velocity portion of the brief. My name's Sean, and I will help understanding the speed in which it takes to leave the Earth's atmosphere. Today we'll discuss the minimum speed required to leave the Earth's atmosphere for any spacecraft that's trying to overcome the Earth's gravity. I'll explain why this concept is critical for space exploration. Understanding escape velocity is a key integral for this portion. The spacecraft's minimum speed is the portion which it takes to leave the Earth's gravity without being pulled back down. For Earth, the speed is around 25,000 miles per hour. The speed is crucial for rockets to reach space, as gravity consistently works to pull the spacecraft back down. What is the escape velocity? Escape velocity essentially is the speed needed to leave the Earth's gravitational pull. For Earth, it's about 25,000 miles, like we said. This will increase with the variety of the size of the planet. So if we were on a different planet, it would go up or down depending on the size of the planet. rockets must reach the speed to be able to enter the space. The formula that it takes for escape velocity is measured here, with escape velocity as v, gravitational constant is g, m equals mass over Earth, and r is the distance from Earth's center to the object. Um, Essentially, this is calculated through the escape velocity, which we'll need to understand a few different factors. As first, gravitation. Gravity is determined as the planet's mass in this case. Earth, which is a very large planet. Second, we'll need to understand the constant, called the gravitational constant, which measures the strength of gravity in this universe. Finally, we need the distance from the center, which is um, the distance between the center of the Earth to the object that's trying to escape the gravitational pull, which in this case will be the rocket surface. Earth's mass is about 5.972 times 10^-45.97, so 10,245.97 times the kilograms, and its radius is roughly 6,371 kilometers. When we combine these numbers through the gravitational constant, we can calculate the spacecraft and the distance and speed that it must reach to be able to leave that atmosphere, um, which is, as we said, about 25,000 miles per hour. As we break down the formula, we see a higher mass depending on the planet velocity. So for example, larger planets like Jupiter would require a much higher escape velocity because they have a more mass and stronger gravitational pull. On the other hand, being further from the planet reduces the escape velocity because gravity weakens with the distance it travels. So the further the rocket gets away from the surface of the planet, the less that number will increase as it gets further away from the pull. Earth's escape velocity is relatively high due to the size and the gravitational pull from the size that we were talking about and covered. Some real-life applications, spacecrafts must be able to reach these escape velocities to leave Earth for space exploration, satellite push-outs, or refueling stations for astronauts. Rockets are also designed with very powerful engines to achieve these types of speeds. Understanding the escape velocity will help planning these space missions in the future, like NASA does. With these real-world applications, these speeds need to be met to just be able to break the Earth's gravity. Engineers designed these spacecrafts to calculate the fuel needed based on this speed, so the amount of fuel needed to be able to break the gravitational pull. Escape velocity also guides missions planning and ensures the rockets can reach orbit, the moon, and other destinations for space exploration. Historical missions like the Apollo and Mars rover are great examples of these as a principal actions to stand by. And that covers my portion of this brief. In conclusion, escape velocity is crucial for space exploration. It does represent the speed needed to overcome the gravitational pull around the Earth. These concepts help guide the rocket development, fuel measurements, and technology needed to plan travel through space to a certain national missions. And that is all I have for my brief.
Hey guys, that was the end of our presentation. I hope you guys like it and understand everything we wanted to talk about for space exploration. And if you guys have any questions, please drop it on the forum and we will answer them as soon as we can. Thank you.